A new type of lawn sprinkler is developed that has two arms of different lengths. The arms lie in a horizontal plane and rotate about a vertical axis. Both nozzles are aimed upward at 20 degrees from the horizontal plane and have an exit diameter of 2 millimeters. The flow to each arm is equal. One arm is 10 centimeters from the pivot and the other is 20 centimeters from the pivot. If the pivot is assumed to be frictionless and the sprinkler delivers 1 liter per minute to each arm, find the angular speed of the sprinkler. So here's a picture of this sprinkler. So notice it has two arms, a short one here, 10 centimeters long, and a long arm on this side, 20 centimeters long. Here's our 2 millimeter diameter exit nozzle, and that applies at both of these exits here. So this view of this lawn sprinkler is a plan view. So we're standing beside this sprinkler looking straight down. So this little plus sign in the middle is the pivot. It's pivoting around that point. And we want to find how fast it turns. So the other thing to realize is that these nozzles here are angled upward 20 degrees from the horizontal plane. So the paper here is the horizontal plane. So that nozzle is tipped up like this, 20 degrees. So it makes an angle of 20 degrees. The center line of that nozzle makes an angle of 20 degrees with the plane of the paper. So how do we go about doing this problem? Well, first of all, we acknowledge this as our given information. No need to redraw this diagram, so we're going to use it. We'll be putting coordinate system, etc. on it as we go forward here. We'll record what we're asked to find, and we're asked to find the angular speed. So how fast it's turning. Our assumption list, and again we'll populate that as we go. Our analysis. So now we go back and discuss how we're going to approach this problem. So this is a rotating system. So we're going to do a control volume analysis, and because this is a rotating system, we're going to be looking at conservation of angular momentum. Now the question hasn't asked us for a torque, but it's asked us for the rate at which this sprinkler rotates when there's no torque in the pivot. Remember, this pivot is assumed to be frictionless. So this is still a conservation of angular momentum problem. So we need to do two things. We need to draw a control volume, and we need to establish a coordinate system. So first, the coordinate system. The center of the coordinate system needs to be at the point that we're rotating about. So the vertical axis going in and out of the page goes through that point, and the origin is at that point. And I'm going to put X pointing off to the right, and Y the other coordinate on the horizontal plane. So notice the XY plane is the horizontal plane, and Z is pointing straight up at us out of the page. So that's our coordinate system. So our analysis, see the coordinate system. And a very important point we have to make about this coordinate system is, even though I've drawn the x-axis aligned with this long arm of the sprinkler, this coordinate system is not rotating with the sprinkler. So at the instant when we're looking at it, the long arm of the sprinkler happens to lie along the x-axis. But if we look at this a second later or something, the sprinkler will have rotated, but the coordinate system does not rotate. You cannot use a rotating coordinate system because that's not an inertial coordinate system. So the coordinate system has to be fixed. So we'll say C coordinate system, and I'll just make a note here, not rotating. So never use a rotating coordinate system in these problems. You'll get into all kinds of troubles. So we have to use a fixed coordinate system. Remember, we can have that coordinate system moving in a straight line at a constant speed, but we can't have it accelerating, and we certainly can't have it rotating because there is acceleration associated with that. So fixed coordinate system. Now we're also going to draw a control volume. So see the control volume. I go back to the diagram. Now again, the principle of choosing a control volume is to place the control surface at places where you know things. Okay, so realize we know the exit diameter of these things. We know the volume flow rate going out of them. We know the angle they're pointing at. So these two exits are going to be important in our control volume analysis. So I'm going to have my control volume slice across those two exits, like that. Now realize the rest of the control volume doesn't really matter how I draw it because nothing's happening on most of this surface. So I draw the control volume like that. Now, this control volume is rotating with the arm. Okay, the coordinate system is not, but the control volume is. And we'll see the implications of that decision as we're working with our equation. So we make a note here, rotating with sprinkler. So rotating with the sprinkler. Now, another important thing I want to point out about this control volume, and I talked about this in a previous example. Remember that many of these sketches that we get for these problems are very, very simplified. If you take a look at this, all that we're being shown here is the two arms of the sprinkler. Well, if you walk out and you look at somebody's lawn, there's a lot more to a sprinkler than that. There must be a base underneath this thing holding the sprinkler in place with a shaft that sticks up that it can rotate around. There's probably a garden hose heading off to the house. That's certainly not shown here either. But the important thing to realize from the point of view of our control volume is we look at this control volume and we see an exit there and an exit there. Well, where's the inlet? There has to be an inlet to this control volume. Well, the inlet is at the pivot here, right? There's a garden hose probably coming from somewhere, and it enters into the base, and then it turns a 90-degree corner, and the water comes up through this pivot and splits into each of these arms. So there is an inlet to this control volume. Just because the sketch is so simplified, we can't explicitly see that inlet to our control volume right away like we can the exit. But we need to keep in mind there is an inlet, and it's right at the center here at this pivot. So we'll be discussing that further as we discuss our conservation of angular momentum equation. So the last thing we're going to do here on the diagram is label these two exits, 1 and 2. And we'll be referring to those numbers. There'll be subscripts on lots of properties going forward. So we've got our coordinate system and we've got our control volume. Coordinate system not rotating, control volume rotating with the sprinkler. So now we want to look at our conservation of angular momentum equation. So that's the full conservation of angular momentum equation. And again, we start every problem with the full equation so we can make sure we don't miss any assumptions, and so we can learn how each of these terms applies in different types of problems. So we're going to do our regular thing here, go left to right and talk about every one of these terms and see what happens to it for this particular problem. And anytime we make a simplification or cross one of these terms off, that becomes an assumption in our list. So first of all, this term. Remember, this is the torque due to body forces. So we go back and we look at our diagram here and we ask ourselves, what do we know about the torque due to body forces? Well, we have a sort of similar problem that we've had in a lot of these things, is we don't really know anything about what this is made of or how much it might weigh or what the mass distribution is in here. So we certainly don't have enough physical information given here to figure out the body force, so the weight of this thing, much less how much torque it would apply around the origin. However, we can say something about that torque no matter what it is. So let's just say that this short arm has a center of gravity in the middle here, and that's probably pretty close to where it is, and the long arm has a center of gravity in the middle. Now it'll be a little bit further out because of the nozzle on the end, but let's just say center of gravity of this one is here, center of gravity of this one is here. And of course this arm is twice as heavy roughly than this one. So the body force is going to create a torque, but notice the direction of that torque is critical here. The torque that it's going to create, so it's going to be pushing down here and down here, but this one is much larger, so it's going to create a torque in the positive j-hat direction, right? If you curl your fingers on your right hand in the direction that this thing is tending to move because of those body forces, your thumb will be pointing in the j-hat or y direction. So we can't quantify the torque due to the body forces, but we can say that whatever it is, it's going to be in the j-hat direction. Well, why is that important? Well, again, conservation of angular momentum is a vector equation, just like conservation of linear momentum was a vector equation. And if we think ahead a little bit, remember what we're asked for here is the angular speed of this sprinkler. Well, this sprinkler is rotating around the z-axis, so it's rotating in the k-hat direction. So even though our conservation equation has three components, in a little while here, as we work with the equation, the component we're going to be interested in is the k-hat component. We're actually not interested in the j-hat component. So even though there clearly is a torque due to body forces, it's in the j-hat direction, and we're interested in the k-hat direction. So right off the bat here, we're going to neglect the torque due to body forces. So I'll just say we'll neglect body forces. If you're neglecting the body force, you're certainly neglecting any torque that it might produce. So we go to our assumption list and we say neglect body forces. And I'll talk a little bit more about that later on when we're talking about another part of the equation. But the reason we'll be able to neglect this is because of the direction that it's occurring in. So that's really exactly the same thing in a linear momentum problem. If you remember our rocket sled problem or our rocket on rails problem, we ignored the weight because it's not in the direction that we're interested in working. So same idea here. So neglect body forces. So we go back and we can cross that term off. Next is the torque due to pressure forces. And again, pressure forces on the control surface. So again, we go back to our diagram always, and we look at the control volume that we've identified. And this is why drawing that control volume is so critical to these problems. And we ask ourselves, what is the pressure on this control surface? Well, the pressure everywhere on this control surface is atmospheric. Remember, there's free jets coming out of here. 2 jets of water, but the pressure in there is atmospheric. So the pressure everywhere on this control surface is atmospheric. So it's not going to have any net force, and it's also not going to have any net moment around the origin. So the torque due to those pressure forces will be 0. Now, a moment ago I talked about the fact that, hey, we got to remember there's an inlet here. So remember, our control surface does cut through an inlet pipe somewhere. Not really shown, but it has to cut through an inlet pipe. Well, the pressure in that inlet pipe will be higher than atmospheric because it's driving the flow through this system. So technically, there is a spot on this control surface where the pressure is higher than atmospheric pressure. But I want to show you something that happens when we're dealing with conservation of angular momentum. We need to remember this term right here, that we're not actually talking about the pressure force, we're talking about the moment created around the origin from the pressure force. So it's fairly clear that the pressure is 0 everywhere on the control surface except that inlet pipe. So this term is 0 everywhere on the control surface except the inlet pipe because the pressure is 0. But at the inlet pipe, where the pressure is non-zero, greater than 0, at the inlet pipe, this R is 0. So notice the position vector from the origin of our coordinate system to the inlet is 0 because our inlet is at the origin. So it turns out that even though there's that one spot where the pressure is above atmospheric, it doesn't produce any moment around the origin because that's where we place the origin. So as a result of those two things, this term can be ignored. So we'll put a a note in our assumption list that we're ignoring pressure forces on our control surface. So ignore pressure forces. Next term is the moment due to viscous forces. So again, we take a look at our control volume and we realize the only parts of this control surface that are in contact with the fluid, or where there's fluid crossing the control surface, is here, and there's no shearing action there. There's no force being exerted parallel to our control surface there or there. And again, there isn't, the same thing's happening at the inlet. The water is just crossing our control surface. It's not moving parallel to the control surface. So we can ignore those viscous forces. So we say that here. So ignore viscous forces. Next thing is the reaction torque. And again, remember, just like for linear momentum, that's the torque created by any solid object cut by our control surface. And again, the only place that happens is at the pivot here. So our control surface must cut through some solid object here where this rotating arm pivots on the base that it's mounted on. So our control surface does cut a solid object, so there would be a torque there. However, this is where this assumption that's stated in the problem statement comes in. If the pivot is assumed to be frictionless. So the significance of that is, even though our control surface is cutting through a solid object there at the pivot, if the pivot is frictionless, then that cannot produce any torque in the Z direction. Okay, so this is free to rotate with no friction, so there's no friction or no reaction torque in the Z direction. So we can actually ignore that reaction torque as well. Okay, so we'll put in our assumption list, ignore reaction torque, or I'll just say here, frictionless pivot. Therefore, ignore the reaction torque. Now, I'll talk a little bit more about that reaction torque here. We're going to cross it off. In fact, I'll do that right away. So that's going to be 0 in our analysis as it goes forward. But realize that if we think about other components of the reaction torque, the K component is 0 because the pivot is frictionless. However, there is a J component. Remember, we talked about the weight here. This side being heavier, pulling down and trying to rotate this thing in the positive J hat direction. Well, what's going to stop it from rotating that way? Well, the base is going to stop it from rotating. Rotating about the y-axis just means this is tipping over, right? And so the thing that prevents it from tipping over is the base. There's going to be some legs or a plate that this is all mounted on. And so this pivot, although it's frictionless, so it can rotate freely around the z-axis, it can provide a reaction torque in the y direction. And so the term that we ignored here, because it's in the j hat direction, it will be counteracted by a reaction torque here in the minus j hat direction. Okay, so if we carried this term through and got the j hat component of it, it would be zeroed out by the j hat component of this. And neither one of them is relevant when we extract the k component from this thing and continue working with it to get the rotation rate. So everything on the left-hand side has been set to 0 by these assumptions that we've made here. Now we come over to the right-hand side and we see our unsteady term. So this is where having a control volume that moves with the sprinkler is a very significant simplification to this problem. So let's go back and take a look at this unsteady term. Remember that volume integral is the total momentum, angular momentum, of everything in the control volume. Well, because the control volume is rotating with the arm, that is a constant. If we look at this situation now, or we look at it 1 second from now when this thing has rotated a little bit, the total angular momentum of all the material in the control volume is the same. So this is a steady problem because of our choice of a rotating control volume. So we can say that this is steady state. And that allows us to cross off the unsteady term. So that's a huge simplification in analyzing this problem, and it's a result of us choosing a rotating control volume. It is possible to do this with a stationary control volume, but you have to keep that unsteady term, and you have to make sure you quantify it correctly. It's much, much harder to do that way. So rotating control volume turns this into a steady problem. So the last term we have here, notice the curious thing that's happened here. We've crossed off all of the terms so far. We only have one term left, so this is going to have to be 0. But the individual parts of this don't have to be 0. So the whole equation is going to just disappear on us here and not do us any good. Now, remember that this has to do with the transport of angular momentum across the control surface, so it has to do with what's happening at the inlets and exits. And we have our 2 exits that we've talked about, but we also have our inlet. Well, what we're going to do here is assume that for each of these inlets and exits, we have a uniform flow. Okay, so all of the properties inside of that integral, if we take a look at it, R, V, rho, V dot n, dA, all of that stuff we're going to assume is constant over each of these exit areas. Okay, and that's a pretty good assumption because they're quite small compared to the distance away from the center. Because notice one of the things inside of this integral here is a position vector, r. Well, technically, the position vector changes as we go from there to there. But we're saying that's a small enough change compared to the total size of the position vector that we don't need to worry about that. So we are going to use a uniform flow assumption. So I'll put that here. So uniform flow, and that allows us to apply the uniform flow assumption to these terms here. So that's what we'll do. So we're ready now to rewrite this entire equation, what's left of it, and apply the uniform flow assumption here. So we're going to have 0 certainly on the left-hand side. We have no unsteady term here, so that's gone. Uniform flow assumption applied to this. So first of all, we have two exits, exit there and an exit there. So we'll put those down. So we have, for the uniform flow version, mass flow rate at 1 times R1 cross V1. So that's the uniform flow version of this applied at our first exit 1. We have a second exit, so that's plus m dot 2 R2 cross V2. So that's our second exit. Exit 1, exit 2. Now we also have an inlet, but let's go back and look at our inlet. I'm not going to write the inlet down here. Why? Because it's 0. Because at the inlet, this R term is 0. So I could write it down here. I could go minus m dot 3, but the R is 0. So I'm not even going to write it down because it's 0. Doesn't contribute anything. So we see here that these two terms are going to have to cancel each other out somehow as we go forward here for all of this to equate to 0. And that's what happens. So the next thing that we do is take a look at each term here and try quantify it for the problem we're looking at here. Now, the first thing that we can do with this equation is realize that the mass flow rate at 1 and the mass flow rate at 2 is the same. Remember, the problem statement said that the same flow rate went through both sprinklers. So we can actually divide this through by that mass flow rate and get rid of those mass flow rates. So now what we want to do is quantify all of these position and velocity vectors. So we'll do the position vectors first. So R1 is equal to, we go back to our diagram here and we put that on. So R1 is a position vector whose root is at the origin of our coordinate system and whose tip is at our exit. Now realize we don't really know what this distance is. So I'm going to ignore that offset there. And actually, if you did a real detailed job of this, it really doesn't have any effect on the problem anyway. So I'm going to just draw my position vector like this. So that's R1. Okay? So R1 is in the minus I hat direction. And it has a magnitude of 10 centimeters. So I'm going to write R1 down like this, minus R1 I hat, where R1 is 10 centimeters. So we'll substitute that 10 centimeters in at the end. So that's R1. R2, likewise, is our second exit. It's in the positive direction, so I'll just draw it sort of like this. That's our R2, and it's in the positive I hat direction, and it has a magnitude of R2, 20 centimeters. So I'll call that R2 I hat. So very important to get the direction of these things correct. These are both magnitudes, 10 centimeters and 20 centimeters. This one's in the minus I hat direction. This one is in the positive I hat direction. Okay, so that's the position vectors. Next thing we need to look at are these two velocity vectors. And here's where we need to be really careful to get these velocity vectors correct. Well, first thing I want to do is go back and take a look at our diagram. And remember, these velocity vectors, key thing about them, they have to be written down relative to the coordinate system, okay? Not relative to the nozzle, which is moving, relative to the coordinate system, which is stationary, which is glued to the ground. So if you're standing beside this lawn sprinkler, it's the velocity you would measure if you stuck your finger in that jet of water, or stuck an instrument that measured velocity in that jet of water, because you're standing on the ground. So velocity relative to the ground. So we go back and we look at this, and we're going to actually look at number 2 first here, just because it's in the positive quadrant here. It's a little bit less confusing. So we'll look at number 2. What is the velocity of the water coming out of that nozzle? Now realize that we're analyzing this thing at a particular instant in time. And the particular instant in time that we're doing this analysis is when this long arm happens to line up with the x-axis. So the long arm here is lined up with the x-axis. So notice that the water coming out of here doesn't have an I component. It certainly has a J component, and remember it also has a K component because that nozzle is tipped up 20 degrees from the horizontal plane. So the water coming out of here has a K component and a J component. So that's fine. Well, what do we know about the velocity of the water coming out of there? Well, remember, we know the volume flow rate and we know the diameter of the sprinkler. So from the volume flow rate and the diameter of that nozzle, we can figure out the velocity of the water coming out of there, but we have to remember that's the velocity relative to the nozzle tip, because this is the rate at which water is coming out of that nozzle tip. So that velocity that we get is relative to the nozzle tip. So we're going to call that VR, the velocity of the water relative to the tip, or relative to the control surface. Remember, because the control surface is moving. So that VR, we can get a number for that, and we'll calculate that a little bit later. But what we need to do is use this VR in order to get the velocity of the water relative to the ground. So that's what we'll do here. So moving on to the next page here. So our V2, we're going to do V2 first. So this is the velocity of the water coming out of an exit 2 relative to the ground. Well, first off, I'm going to work on the J component of it. So we begin with our velocity relative to the nozzle, and we realize that that velocity relative to the nozzle is up at an angle at 20 degrees. So to get the velocity in the J direction, we need to take VR cosine 20 degrees. And I'll just put the 20 degrees in there. Okay? So that's now the component in the J direction. There's another component that we'll write here in a moment in the K direction. That's the component in the J direction. Now, the problem is that's the velocity relative to the nozzle. We need to subtract from this R1 omega. Why do we need to subtract that? Because at this instant in time, that nozzle is moving downwards in the negative J hat direction. And what speed is it moving at? Well, it's moving at R omega. Notice this thing is rotating in the clockwise direction, so the velocity of this nozzle tip is minus r omega. So to get the velocity relative to the ground, we have to subtract minus r omega from this. Okay? So let's just see if this makes sense, if we've got the signs right here. Let's say that the sprinkler was not rotating. You reached down and you grabbed onto the arms and you stopped it from rotating. So that's gone. Well, then the velocity relative to the ground, at least the j component of it, would be VR cos 20. Okay? Let's say that the sprinkler was actually rotating fast enough that r omega equaled VR cos 20, so that this is 0. So what that means is the water would be coming out of the nozzle, but just dropping straight to the ground. It would be not moving relative to the ground at all. Okay? So this makes sense. That gives us our j hat component. Now, what direction is this thing in? Well, this is in the positive j hat direction, right? So I need to take this, it's not a vector yet, but I need to multiply that by j hat, give it the correct direction. So that's the j component. Now we're also going to acknowledge here that there is another component. So the other part of this, VR cos 20, is in the j direction, VR sine 20 is in the k hat direction. And notice that nozzle tip is not moving in the k direction, so we don't have to do any shift or any correction to get the frame of reference right. So this is just VR sine 20 k hat. So we are assuming here that this sprinkler is moving in the horizontal plane, and it does say that the arms lie in a horizontal plane, but we're going to put that here too. And we're really making that assumption when we write down these components of this vector like that. So that's V2. V1 we can do a little bit quicker because it looks very similar. V1, same thing's happening over here, VR cos 20 degrees. Minus, again, R2 omega. So different radius because that's a shorter arm. And this velocity would be in the minus j hat direction. If you go back and look at the diagram, you'll see the water is coming out there in the minus j hat direction. So the only difference there is different radius here and different direction. The k component is exactly the same. So that's our velocity out of exit 1, velocity out of exit 2. So the complication here is making sure you get these velocities relative to the ground. Now notice, this is the spot in this solution where omega comes into the problem. Remember, omega is what we're looking for, the angular speed of this thing. So finally, omega is actually showing up in our solution. So the next thing we need to do is bring this all back into our equation and take those cross products. So we'll just show our equation assembled here. So 0 equals So now I'm going to write this equation out, and I'm taking these cross products, okay? So we've got R1 cross V1 and R2 cross V2. And I'm just going to write the result of that down here, okay? So I've started it here. This is the first part of that. Next part will be like this. Cross products have been taken there. Now we're going to extract just the k component. Realize it's only the k component that has the omega terms in it. So there are two j hat terms here, there and there, but we're going to take only the k component of this. So extracting just the k component. And again, it's because we're interested in rotation around that axis. So the k component says 0 equals R1VR, and we'll just write the rest of this out. So we just need to solve this equation for omega. So rearranging this, isolating omega, we get the following. Like that. So that's our equation for omega. And it's depends on the angle that those nozzles are tipped at, the velocity of the water coming out of the tip, and these two radiuses, so 10 and 20 centimeters. So the only thing we don't know here yet is this VR. So we'll figure that VR out next. So where do we get the VR? Well, we know the volume flow rate and we know the area of the nozzle. So VR is going to be equal to the volume flow rate, and the volume flow rate is the product of velocity and area. That product is actually given to us, divided by the area. Okay, so we could put numbers in there. So we were told the volume flow rate is 1 liter per, 1 liter per minute. So a liter per minute we need to put in here. Well, we need that in cubic meters. So a liter, there's 1,000 liters in a cubic meter. So there's 10 to the minus 3 meters cubed. That's our liter, divided by 60 seconds, because it's a liter per minute, and we need this to be in cubic meters per second. So that's our volume flow rate. And then divide that by the cross-sectional area. So pi by 4, and the diameter was 2 millimeters. So 0.002 meters squared. So that'll give us the velocity. And so that comes out to 5.3052 meters per second. So about 5.3 meters per second coming out the tip. So now we have all of the numbers we need to solve for this omega. So that's what we'll do next. And we calculate that out. We get omega equal 29.912, and this will be in radians per second. And if we convert that to revolutions per minute, we get 286 revolutions per minute. So the sprinkler will rotate at 286 revolutions per minute. So just to recap some of the important parts of this problem, it's an angular momentum problem, and it's very important to realize that the conservation of angular momentum equation is a vector equation. So there are 3 components there that you're working with. The way we've set up our coordinate system here, we're really only concerned with the k, or the z component. That means that the body force and the torque can be ignored. And the other key thing here, coordinate system has to be attached to the ground, and the velocities of the fluid coming out of these exits has to be written relative to that coordinate system, relative to the ground. And those are some of the key things to remember in doing problems like this. So thanks for watching.